Good morning and welcome to the technical sessions on the second day of OLAB 2022. Um, today is this is technical session 3 after the 2 sessions yesterday, and this session is going to be chaired by Professor Shamarjit Kaur, who's also the program chair of this conference. Let me introduce you to him. Shamarjit Kaur is Professor Shamarjit Kaur is a graduate of Presidency College with postgraduate degree from University of Calcutta, and he earned his PhD from Vidyasagar University. He is currently a professor in the Department of Mathematics, National Institute of Technology, Durgapur, India. He is also an active participant in Chinese academia, having served as a visiting professor at Tsinghua University since 2009 and as a co-investigator of 2 sponsored projects funded by National Science Foundation of China at Tsinghua University and Nankai University, and has delivered more than 20 invited talks at various Chinese institutions. His academic collaborators, co-authors include academics from China, Poland, Norway, Canada, Serbia, Lithuania, and Turkey. His current research interests include operations research and optimization, soft computing, machine learning, and uncertainty modeling. He has been the doctoral dissertation advisor to 25 students as of now, and 6 students are currently working under his supervision. We are honored to have him as session chair, and I request Professor Kaur to begin the proceedings, sir.
Thank you. So, good morning to all of you. Welcome back for the second day fast session, that is technical session 3. So, in this session, we have 2 presenters, Professor Oscar Castillo and Professor Mohan Choudhury. So, first, good morning, Professor Castillo. Can you hear me? Hello?
Yes.
Okay, thank you. So, let me introduce Professor Oscar Castillo. Oscar Castillo holds the doctoral degree in science, in computer science from Polish Academy of Science. His dissertation title was Subcomputing and Fractal Theory for Intelligent Manufacturing. Currently, he is a professor of computer science in the graduate division at the Tijuana Institute of Technology, Mexico. In addition, he is serving as research director of computer science and head of research group Hybrid Fuzzy Intelligence System. Currently, he is the president of HEPSA and past president of International Fuzzy System Association. Professor Castillo also chair of Mexican chapter of Computational Intelligence Society, IEEE. He also belongs to the technical committee of fuzzy systems of IEEE and the task force of extensions. Members of IEEE. He belongs to the Mexican research system. Fuzzy logic, fuzzy control, and neurofuzzy system. He has published over 200. So with this, we can start our technical session. Professor Castillo, please.
How much time do I have?
So 35 minutes. Please try to complete your presentation by 35 minutes.
35 minutes. Okay, thank you.
Thank you.
Can you see the screen? Can you see? I don't know if you have the full screen now.
You can see the full screen. Yes.
Yeah, okay. Okay, thank you. So I will speak today about type 2 and type 3 fuzzy systems. Very briefly, just to give you an idea of this area of research. These are my achievements. I have over 1,000 papers, more than 60 books, more than 100 students I have supervised, and other than media, I don't know, Professor Carr, in his introduction, what he mentioned, because I couldn't hear, but I guess it was a nice introduction, and I want to thank him for inviting me. This is the group in Tijuana, the research group. And I will start with the beginning very briefly. Of course, Professor Sade in 1965, he proposed the idea of fuzzy sets. Actually, type 1 fuzzy sets was proposed at that time. And his idea was extending the original concepts of mathematics, which can be labeled as type 0, because using this precise number in the models, we will have like a type 0 model. And when we go into using fuzzy numbers instead of real numbers, then we will have type 1 fuzzy models. But later he extended to type 2 also. He proposed in 1975 type 2 fuzzy sets, because he realized that type 1 was not sufficient to represent uncertainty. So he did propose type 2, although it was not so much popular at that moment until around the year 2000. Professor Mendel and some other people started working on type 2 really. And before that, there was not too much work. And now at this moment, we have seen, we have witnessed that these type 2 fuzzy systems, both kinds, interval type 2 and general type 2, I will make the distinction later in my talk. Both kinds of type 2 have been successful in real applications, going from control, robotics, planning, cognition, time series predictions, just to mention a few of them. And real applications also require that we optimize these fuzzy systems. So actually, usually we need, for example, a meta-heuristic optimization method to optimize the parameters and also maybe the structure of the fuzzy system to have the real applications, successful real applications that we want. Even with this success, we still don't know if we will require higher types because there are more complex problems that we haven't yet tackled. So in this regard, is that we have started research on type 3. So we are beginning on type 3 from last year to this year, and we will see in a few slides some of these achievements in type 3 also. Anyway, we will start from the original concept. Of course, traditional sets or CRISP sets only allow membership or non-membership, or using numbers 1 or 0, only 1 or 0 to represent the belonging or not belonging to a set. But Professor Sade in 1965, he proposed that membership should be given any value between 0 and 1. So values that are close to 0 will represent that we have a low degree of membership, and values higher and closer to 1 will represent that we have higher degree of membership, but you can have any value between 0 and 1, not just these two values that are usually considered in traditional sets and in traditional mathematics, of course, also. But even with this extension, that of course generalizes all mathematics, because if we change the concept of a set, we change a crisp or traditional set for a fuzzy set, then all mathematics can be generalized. But even with this extension, later we did find that there was not a complete, this was not a complete model of uncertainty. Really, mainly describing the vagueness of the concepts, not the uncertainty. So that's why the same Professor Sade proposed type 2 later, and of course this was developed even later by Professor Mendel and then others after that. Anyway, let me show you the difference. This is a very simple example of a type 1 fuzzy set representing the concept or the word tall. Tall, of course, is a subjective concept because it means different things for different people. So I could have my interpretation or my perception of tall, which will be different from other people. But if we try to use a type 1 fuzzy set, in this case, a triangular type 1 fuzzy set for representing this concept, we will arbitrarily assign numeric membership values to each particular height in meters. So for example, here 1 point in meters, if this is my perception or my interpretation of tall, we'll be given a membership of 0.62. And different values of height will be given a different membership. But this membership is only maybe my interpretation. Other people will have other values. And so if we arbitrarily use these parameter values for designing our fuzzy system, it's possible that this will not represent the uncertainty, the real uncertainty that this concept has in real world. And so that's why we needed type 2 fuzzy sets. So basically in a type 2 fuzzy set, we will not be giving a precise value to the membership. Like in this case for 1.8, we give a 0.62 in the type 1 fuzzy set, which is, of course, this is an improvement over a classical set, because in that situation, we only could consider 0 or 1. But really, as I told you, as different people will have different meanings, or the semantics of this word is different for different people, then, for example, in the first situation, if we try to use interval type 2 fuzzy sets, what we will do is to use an interval around 0.62, containing 0.62, to represent the different memberships that could be given by different people to this particular example. In a more general case, and this is the reason of using generalized or general type 2 fuzzy sets, this is the name for these fuzzy sets, we will really use a fuzzy set again to represent the uncertainty over the membership. So each value of a domain will be given a membership, or a fuzzy set will give us a membership, instead of just having an interval like in that case. And this will be the full model of type 2. Mathematically speaking, this is the mathematical definition of an interval type 2 fuzzy set. So in this case, as you may recall, in type 1, we only have this pair, X and U, the elements and the membership. But now we will have a secondary membership. But in the case of interval type 2, this secondary membership will be fixed to 1. When we will go later to general type 2, here we will have another membership function, another function here, instead of just having a value of 1. Anyway, but for the moment, let's consider just having a fixed value of 1, or this means uniform secondary membership, like considering that the uncertainty over U is uniform in this case. Using this, we will have a better model than type 1, but not the complete or full type 2 model, like I was saying. But in this case, we have something very interesting. We have that the membership function for tall, now the triangular membership function in the case of interval type 2 will be like this, in which we will have an area called footprint of uncertainty, the FOU, representing the different meanings that different people will have for this concept. So you can imagine here having an infinite number of triangulars inside or embedded in this type 2 fuzzy set, interval type 2 fuzzy set. The limiting ones, the limiting type ones will be the lower membership, which is inside here, and the upper membership function, which in some way characterize, because they are the limits of this interval type 2 fuzzy set, the upper membership and the lower membership give us a way to convey the uncertainty of the concept in this case, or the subjective meaning that this concept has. So in this case, for a particular height, then we will have an interval membership. So here, for example, will be the membership of to tall of a person with 1.8 meters of height will be between 0.42 and 0.78. So this is the difference. We will have an interval as the membership in this case. What happens when we do this? Of course, the advantage is that we are representing better, in this case, the uncertainty of the concept or the meaning of the concept. But of course, this will cause problems on the other hand, because computing speaking, we will need to do more computation to use these type 2 fuzzy sets, meaning that usually in the applications, we need to falsify first our information, then we reason with it, then at the end we defacify. But in the case of type 2, the falsification will have two parts. First, we will make a type reduction, which will lower from type 2 to type 1, the fuzzy set. Then after that, then we will apply the usual defalsification, for example, centroid, to reduce from type 1 to type 0. And this has the meaning that we will have like an extra step in the output to give a result, to provide a result. And actually, both steps are like weighted average, similar to weighted average. A weighted average like the one shown here will be needed to approximate the type reduction. This will be done for a sample of points inside the type 2 fuzzy set, and then we reduce it to an interval, and then we can do the average to defalsify and obtain just a number. So that's the way that we need to solve. We need to do this to solve the problem. But this in practice will require a lot of computing, because we will need, for example, 100 embedded type 1s inside to approximate or something like that, if we do this by brute force. But fortunately, Mendel and one of his students, Liu, they did find theoretically that only 2 special embedded type 1s are sufficient to approximate the interval type 2. What they did find is that we need to find 2 points, 2 switch points are called, left and right, which basically are called switch points because in these points we switch from the upper to the lower. The red one is part of the upper, and then you switch to the lower. The green one is part of the lower membership function, and then you switch to the upper. So these special particular type 1 membership functions are the ones that we will need in this case to approximate an interval type 2. And with this, we can solve the problem. And later, of course, they did find, Karnik is also another researcher that worked with Mendel. He's from India. They find an iterative algorithm to approximate the switch points and then basically be able to compute the type reduction and then the falsification. So this in practice with 3 to 4 steps will give a sufficient good result. And basically, in practice, this was sufficient to be able to, for example, produce real-time control with hardware implementation even faster. And so this actually solved the problem at that moment. And the general view of this kind of interval type fuzzy system is like this. As I mentioned, usually we will have inputs coming in. For example, in the case of a robotic system or a vehicle, we have sensors measuring velocity, distance, and so on. And these values are falsified, meaning we have memory chip functions in the fuzzy system that will interpret these inputs as low, high, or small, or far, or near, for example. We have memory chip functions for that. And then we have rules to, for example, drive the vehicle or control the robot. The rules will have the knowledge of the experts saying if we are near, we will, for example, apply brakes or things like that, and so on. But these results will be fuzzy, type 2 fuzzy sets in this case, and then we will need reduction, like I was saying, from type 2 to type 1, and then declassification to from type 1 to type 0. Now, if we go one step more in the generalization, if we use general type 2, instead of having this memory chip function as before here, we had a value of 1, fixed value of 1. Now we will have another function to give us for each value in the domain of the primary member chip, the secondary member chip, representing the uncertainty over the numeric possible values. Instead of the numeric values, sorry, we will have a member chip for each point, and in this way represent the uncertainty of the concept. So the representation now is three-dimensional. You can see in this plane, for example, this will be the interval view for a particular X, but now we will have coming out of the screen a secondary member chip function that will give us different secondary member chip for each point, for each value in this domain. So it's not uniform. In the case of interval type 2, this was supposed to be uniformly value of 1, so we didn't need it to consider this other dimension. But now, as this will be another memory function, we will need to consider. But computations are even more, in this case, heavy, because we have that we need, for example, to apply alpha cuts horizontally, and then we will have for each cut an interval type 2. And then we need to perform the union of the results of different interval type 2s to approximate the general type 2. And of course, mathematically speaking, we will have, although I will not go into detail about that, we will have that these new kinds of fuzzy sets require extensions of the operations. For example, instead of union, we have the join, and instead of intersection, we have the meet, which are done for different values inside the footprint of uncertainty, and not the simple union and intersection that we have for real numbers. So, and with this, all mathematics is extended. So we could have type 2 fuzzy differential equations, type 2 fuzzy algebra, and so on. All mathematics can be generalized in this way, although I will not go into that. And going in visualizing, what we are doing is something like this. For example, in applications, if we use a particular number, here I am showing the general type 2 with different grades of color instead of using the third dimension, but it's the same thing. We can have for particular inputs, we calculate the outputs, and then we do the union of the outputs to obtain this, and then we perform time reduction over this fuzzy set, type 2 fuzzy set, and then declassification to obtain the result. Or that was with singleton values in the inputs. If we use non-singleton, meaning using fuzzy sets as the values coming in the type 2 fuzzy system, the same idea, but a little more complex, because we are using fuzzy values instead of numbers as the inputs. So we have to do similarly the computation, although I have to say that not many people use non-singleton type 2 because it's more heavy, computingly speaking, but at the moment, I mean, so this is an area of research that is worth investigating. Not too many papers on non-singleton at the moment. Anyway, I will say that very quickly that we have compared results at the beginning, of course, around 2009, 2010, people were skeptic about type 2, and we needed to show that type 2 could give better results than type 1, even if it was more time consuming in the computer. The results will be better. And we show in control, I will be very quick about this. In control, usually we use the error in change of the error, for example, of the velocity that we are measuring, for example, in a car, to control, for example, the cruise controller we all have in our cars at the moment. If we want to maintain a velocity, we can use the cruise control. Basically, cruise control functions as I am saying here, is measuring the error in velocity, difference in the velocity that we have with respect to the velocity that we desire to have. And also the change of the error is the difference between the error in the past and error at the moment. And we control the accelerator with these two inputs. So we have fuzzy rules. This is the fuzzy controller, fuzzy rules. Like any of us will drive a car to maintain a velocity. We can see us as the experts in this kind of a problem. And fuzzy rules will be used here. Here we have the vehicle. We measure velocity, and then we send here to compare the velocity that we are measuring to the desired velocity that we want to have. The same thing for temperature or for other things. But in real world, we will have noise here. When we send the signal from here to here, noise will be present. For example, Gaussian noise. In here, we use, for example, a mathematical model of the system. And we can measure the errors. There are different metrics of the errors in control. If we compare under assuming that there is no noise, ideal situation, the difference between type 1 and type 2 will be not significant. But if we consider real situation where there is noise present in the feedback, then we will see how type 2 errors are very low compared to type 1. Here is the plot for comparing under no noise. In this case, no noise in the control feedback means that we don't have uncertainty in this. Uncertainty is different thing in different applications, of course. But in this case, is noise in the feedback. And if we have noise in the feedback of the controller, then you can see, for example, in the lowest figure here, in the low, in this metric, the errors of the red one, which is type 2, are lower in all simulation for all these times. Almost all times is the red is lower than blue. So if we sum the errors, of course, the error will be lower for type 2 than for type 1. And this is for a particular level of noise. If we increase noise, difference is bigger in favor of type 2. If we decrease noise, then type 2 tends to be as type 1. This is just the numbers. We also have developed our own toolbox. Now you can see in MATLAB a toolbox for type 2 for the first time in 2020. I think it appears for the first time in MATLAB. Before that, they didn't have a type 2 toolbox, only type 1. But even this type 2 toolbox is only for interval type 2, not for general type 2 at the moment. Anyway, we developed our own toolbox, similar to the one for type 1. I should mention here that in type 2, we have more parameters for the membership functions because of the footprint of uncertainty. So the design or the optimization of these systems is more complicated than in type 1. So that's why we need optimization like with metaheuristics. And we can develop our own type 2 fuzzy systems, interval type 2 fuzzy systems, for example, like this. This is for the shower control, controlling the cold and hot water. Very simple problem, but even this problem is non-linear. We can develop our membership function, the fuzzy rules to control the two valves in this case. And even in this problem, we can see that type 2 is better than type 1. Recently, we have developed in theory many things also, not just applications. We have, for example, developed formulas, closed form formulas for computing type reduction And in this way, avoiding using iterative Karnik-Mendel, we have applied type 2 for controlling parameters in meta-heuristics, fuzzy control of the parameters in meta-heuristics during execution. We have shown that type 2 fuzzy controllers are more robust because it's like having an infinite number of type 1s inside because of the footprint of uncertainty. So each of these type 1s will be able to respond to different situations, and in this way, robustness is achieved, and we can have higher degrees of noise, and type 2 will still be able to control a real system in where type 1 will fail. We have used shadow type 2, combining shadow sets, which is a concept from Professor Witold Pedrich, to achieve only using two interval type 2s to approximate a general type 2. Similar to using when we are using two type 1s to approximate an interval type 2, we want to use like two interval type 2s to approximate a general type 2, because if not, then we will be using hundreds or thousands of interval type 2s to approximate a general type 2, and that will be very time consuming. Mathematically also, we have used integration, numerical integration for methods, or to integrate alpha planes in general type 2 to also increase velocity of computation in type 2. Also using, for example, sampling a problem in diagnosis, medical diagnosis, we can develop many type 1s, in this case type 1 classifiers, like to construct or build the footprint, the general type 2 footprint of uncertainty in this case. Also optimize the footprint with, for example, particle sum optimization. And lastly, I will say very briefly a few words about type 3. Now we will one step further. You remember we only have before in type 2X, then the primary membership, and then the secondary membership. Now we have a tertiary membership that will give us the uncertainty over the secondary. And here, actually, this is the representation of general type 3. But at the moment, we are for practical purpose, we are using this tertiary as 1. Like when historically in type 2, we use the secondary as 1, and we had interval type 2. Then we are able to compute general type 2. Now we are at the moment using this tertiary membership as 1, fixed to 1, to have interval type 3. And we have this kind of representation for this interval type 3. These are the alpha cuts, horizontal, even as alpha planes, and we can construct the footprint, the green function here, for the different values. In this case, this is only for X prime here. And the operations, again, can be generalized: union, two fuzzy sets, intersection, negation of the union, and so on. Mathematically, we can develop all operations and then go on to generalize in mathematics. And we have shown that in control, this works well. We have a paper in last year in Journal of Fuzzy Systems that showed that for controlling temperature in simulation and also in real system, type 3 show better results than type 2 and type 1. This was by my colleagues in Iran. More recently, this is for controlling voltage in microgrids, and published this past month in Applied Soft Computing. This is for prediction of COVID, combining interval type 3 fuzzy system with fractal dimension for measuring complexity of the time series as information in the fuzzy system. Also for quality control and sound speakers that are being manufactured. Here we are using the experts to give us the rules of evaluating the quality of the speakers being produced. And also for designing controllers. In this case, we tested an interval type 3 fuzzy controller for a mobile robot, but also we optimized it with an interval type 3 fuzzy differential evolution method that we have proposed. And also for B-colony algorithm we have a method where we use rules to control the alpha and beta parameters of B colony to increase the convergence, or improve the convergence of B colony for optimizing a controller. And also we have done this in real systems. I think this is mostly what I wanted to show. This is just the architecture of the controller with the sensors in the output. And we have comparison of the errors for trajectories, and also we reduce the error in the time to perform a complete circuit for the robot in simulation. This is but also in real system. And also with my colleagues in Turkey for helicopters. This is for a mini helicopter, the controllers of the tail rotor and main rotor. And here are the fuzzy rules of the experts. And at the moment we have tested with this system in the lab, which has here the two rotors, but in future we will test with the real helicopter. Here are the comparison to PID, and we have lower errors than PID. So in conclusion, hope I can motivate you to study this area or to do research in this area. I think there are many things to do in theoretical part and also on application side. In my group, there are people working on parallel cognition, time series prediction, medical diagnosis, and other areas, but I mostly work on applying on control, although I collaborate with them, so I have papers also with them. And if you have any questions, you are welcome to ask it. I guess if there is time, I don't know if there is time. Thank you very much. I guess there are no questions.
Sir, can you hear us?
Yes.
So, yeah.
So, hello, Professor. Have you developed that type 3 toolbox for mobile?
No, at the moment, sorry. We have some code, some programs that we have done for this this type 3. This is what we used to show these figures that I did show from type 3. And but this is not like a toolbox. Still, we have only the code, separate codes.
Okay,
at the moment.
okay. Actually,
we are testing.
Yes, thank you. Actually, we have used your type 2 toolbox, so that's why I'm asking. Thank you for your nice presentation. So it's a big clap to Professor Castillo.
Thank you very
sir.
much for the invitation. Thank you very much.
Thank you. Thank you.
Okay.
So we now start our next presentation. So our next presenter is Professor Mohan Choudhury. Professor Choudhury? Hello? Professor Choudhury, can you hear us? So, okay. So let me first introduce Professor Mohan Choudhury. Professor
Mute,
Mohan
yeah.
Choudhury.
Yeah,
Yeah,
right.
thank you, Professor. So Professor Mohan Choudhury received his PhD degree from Kurukshetra University and
You
then
want me to
moved.
share screen? No,
Just,
share screen or what?
just wait, sir. Just wait 1-2 minutes, sir.
No, I clicked that. We are sharing. Right?
Okay, you can share. You can share. So Professor Choudhury received his PhD degree from Kurukshetra University and then he moved to Canada for a senior postdoctoral fellow at University of Toronto before moving to the Royal Military College, Canada in 1967. So since 1967, he has been
Professor,
in the
right?
Department of
And say
Mathematics.
share. No, click share.
Yes. Computer science at the Military College of Canada. He currently holds the position of a professor in the Department of Mathematics and Computer Science. He served as the head of the department from 90
You want
to
me to put on the
91.
screen? Start
Yes.
my slide.
Yes, you start your slide.
This one.
Yes, it is visible.
No, we can increase it. We can increase it like no.
Full screen. Sir, please switch on your video.
Video. I don't. This one. Okay.
Yes.
Click zoom. Or start videos. Videos here.
No, in the YouTube.
Yeah. Okay.
Okay, it is coming.
Start my slide or not yet? Okay.
Okay, sir, let me start.
Oh, you want me to go to Skype? Here. Yeah.
Yes, now it's visible. Yes, it is visible now.
Click Skype. Yeah, Skype, I'm clicking. Oh, go up. Click this. Number 2. Okay. Button, which one? Oh, this one. Stop it. Skype, stop it. Okay. I clicked. I'm clicking. No, I am clicking Skype here. Or maybe here, Skype here. Cross it. Okay. What happened? Okay.
Video has sent. Okay. Sorry for the little delay.
No, that's fine.
Yeah, it is fine, sir. So Professor Choudhury has held and continues to hold position as an associate editor for the several operational research journal. He's organized and session chairs for various organizations. In 2003, Professor Choudhury contributions were recognized by the Canadian Operational Research Society that gave him the award of merit. In 2005, he was given the service award by the same society. Also in 2005, his paper and interference relation and a unified method by the derived scenario scheme lengths was just adjudicated by the best paper of that year in industrial engineering by the Korean Federation of Science and Technology. With this short presentation, I welcome Professor Choudhury in this keynote session. Professor Choudhury, please, you start your presentation.
All right, thank you very much. You want me to put the slide on?
Yes.
Should I start?
Yes, Professor Choudhury, please start.
Okay. Yeah, everybody welcome to this talk. And this is my university or college, we call it, but it's really a university. We have master PhD program, just like we have Imperial College. So this is called college, but it's a full university. And this is the abstract which I sent earlier, so everybody must have it. And that gives you that lot of mathematicians like Kendall, Kleinrock were talking about the difficulties in finding the roots. The solution by roots is very easy, very important. So that's what we will be talking about first, the roots. And then I will be talking about how to use this method in solving queuing problem and many other problems can be solved. So this is the abstract and numerical inaccuracy, all those problems we have resolved those. Here you can see one of the example for queuing and at airport. So the procedure will be like this. It consists of 3 parts. The first part will deal with root finding, starting with the linear equation. The second part will show how the students have gained from my lectures and they talk about me and all that. The third will be applying that method to queuing problem. And in fact, we'll see the method can be applied to many problems, whether you are in algebra, economics, chemistry, physics, calculus, root finding occurs everywhere. And there were problems. Now we have finally resolved. And here is the history, a little bit about root finding. The first is the linear equation. Then the second is the quadratic equation. And the contribution by Egyptian, Greek, then even by Indian, Brahmaputra period and all that. So there is a long history, and you can see down there that some people from Iraq contributed to the simple cases, the quadratic equation. First solving by geometrical method, then algebraic method. So here's a little bit of history. Next comes the cubic equation. The cubic equation, here the Italian mathematician made the contribution. Quartic is also Italian mathematician. The Ferrari, he also started work as a servant and later on contributed to mathematics. So this is just like our prime minister is known that he started the work as a chaiwala and now he's prime minister. So here's the history a little more about the this little bit, no, here. The quintic, the 5th degree. Now, Norwegian mathematician, he contributed to this. And after that, the Nobel Prize was created. And one of our Indian, S.R. Srinivasa Vardhan, he got the Nobel Prize. And that carries a big amount like $1 million. He got the Nobel Prize. I think this side is a little bit covered. So uh, this side, maybe some part of it you cannot see on the right side. So here is the fifth degree equation. So this is Abel who tried to solve it, but we cannot solve it analytically. And therefore we go for numerical work. So in some cases we need the analytic work, but bigger equation we cannot solve analytically. And in many applications, we really need to solve it numerically and use that number to solve the problem. So Abel is the one Norwegian mathematician who contributed to this, that we cannot solve this analytically. So here is the story about Abel. Here's the one. And now we are coming to general equation. Every complex polynomial equation of degree n has n root. So that's what we are going to talk about. And many mathematicians or many books have been writing that we cannot solve those numerically. So that's what we'll be talking about today. And then its application to the queuing problem, which are mathematically very complex. So here is talking about the analytic solution. And I talked about earlier. Then we are going for numerical solution. So some numerical solutions were given by Laguerre, Muller, Jenkins-Traub. They gave the numerical solution. But still, there were problems. They could not be solved, as I told you in the abstract. Everybody was complaining they cannot be solved. So here is in the 1960s. So the queuing problem was left in generating function. So the generating function is like Pz, where Pi is the probability Z to the power I. So that, and similarly Laplace transform. So the solutions were being left in generating function or in Laplace transform until somebody came that how can we use it? So that's how the numerical work started. So some comments made, I told you earlier, Candle says the solution is left in the form of a Laplace transform. So queuing theory reveals the Laplacian curtain. Kleindard made similar. The most difficult parts is using spectrum factorization. He started to use the eigenvalue, but the same problems occur in eigenvalue as in solving polynomial. But now we will be talking about not only polynomial, any equation we can solve for roots. So here comes another mathematician, Newtz. So Newtz made a comment that when the roots are too close to each other, it's difficult to solve them. And he gives the example of Cromlin. So Cromlin was dealing with a queuing problem, MDC. Now, people who do not know queuing, but I can explain this notation is the arrivals to queuing is by Markovian process. That is this. Service is deterministic, is fixed time. And there are C servers, as I showed you that example or the picture before. So he makes a comment in Newtz that Cromlin was solving this, and he made the comment, Cromlin, that when the roots are too close to each other, they cannot be found. He made the comment that Cromlin made comment at that time. My mathematician now even do not know this. That's the comments Newtz made. And since the roots could not be found, so they started another method, which we call now matrix analytic. In fact, the matrix analytic means the arrivals are correlated and service is correlated. I gave the initial solution to arrivals correlated, arrival service correlated, long back in my thesis, 1965. Then later on, this became, here are the references. Later on, this became Markovian arrival process, Markovian service process. That's what Newtz introduced. But later on, I will show you that even that is much more complex. And the roots, because they could not solve, I solved that problem, and roots takes over that even. So let me go a little bit here to some example. Even recently, this gentleman here is also saying that if the equation is this type, now this AMZ is a complex equation like this. So if the equation is this type, and if M is large, then it's difficult to find the roots. Even at 2004, that's the comments some people are making here. And this shows here the number of arrivals, which is Poisson process, during some service time. Service time is arbitrary here. So K arrival during service time of type J. So this is a very complex formula. And the gentleman here dealing with this makes a comment that it's difficult to solve for M root. But the method I gave, now we can solve almost any equation. So here are the references. And that's the comment he is making. When M is large, it's difficult to solve. And here the further history about that. At the early stages, I started this trying to solve an invert transform. The queuing problem are in terms of the transform or generating function. And the generating function take the form of a rational function. And rational function, do we need to find the root? That's where the roots come. So here is where, when I gave the method, Maple and Mathematica could not solve a large number of. So at that point, that's where I gave the method. In fact, the work started somewhere in 1985 with my student here, Brier. So I gave him the problem, and that's where we started to solve the root problem. Now, here is the solution, the first problem, which we tried to solve by using roots. And again, M comes the arrivals are by a Markovian process. G is services has a arbitrary distribution. Y is the batch size of service. So whatever the service is, it takes a random batch size. Y is the random variables, so random batch size. That's where the work started here. And then it was published in a nice journal, Journal of Applied Probability. A lot of comments by the referees were very good. Those are the comments. And these are the original QRoot software. And the numerical issue, then we solved this problem. In this problem, again, M is always Markovian process. G service is arbitrary, and B is the size of service, variable up to B, but D is fixed size. So this also was published in a nice journal, and many comments came on that. So now we go to earlier problem. A lot of books have been writing that it's difficult to solve these problems. For example, the first equation. Now, analytically, you can see we can solve it. Z is equal to 1, Z is equal to, these are the roots. But when you go for numerical work, the book says it's difficult to solve this. The next is more complex problem here, which again, we can solve this, all these I can solve. Here is another problem, which is I is the imaginary number. The equation is this. And that's again, their books are saying, these are the references. Books are saying difficult to solve this, difficult to solve this. But now we can solve all those. Here is another example. So all the references are there for these, which they are saying these are difficult to solve problems. Now here comes the real queuing problem. That's where we started. If the equation is, of course, this equation I gave, this is easy to solve. Z to the power 50 is equal to 1 over 100. We have now 50 roots here. It's easy to solve this one. But when the equation changes like this, these are the type of equations occurring in problems I mentioned here. And then even which involve the sine Z, transcendental function. Then we have exponential function. We have exponential function here. So all these problems now we can solve through. And I'll show you later that the matrix analysis method introduced by Noops, the roots problem takes over, gives very simple solution. The math behind that is different. But once the math problem is put into the form of a mathematical form in terms of finding roots, root finding is now very easy. So here gives the example that how the roots, this is now before Mathematica and Maple could not solve. But now we can use Maple and Maple can solve those problems. Even we can now find repeated roots. So here I give you the example that, and here I give you the notation for Maple. F solve, F is the function, X is the variable, whether roots are complex or real, it will solve for roots. So this is how the Maple is solving this equation. And you can see the roots are repeated. Now here I'm giving you a little information about correlation. When the arrivals are correlated, our service is correlated. So that was the when I wrote my first thesis, I gave this idea of using correlation in queuing problem. So later on that becomes the Markovian arrival process and the Markovian service process. And here is what you can see the roots equation. Now, here we are trying to solve this problem. So G, I mean the interarrival times are independent, identically distributed, and a general distribution, not any particular distribution. X stands for the arrivals are coming in batches. The service is geometric distribution. Now in queuing, we have two types of discrete type queuing and continuous time queuing. So in continuous time, instead of geometric, we use M, which is a Markovian again, or exponential. And C is the number of servers. So this is dealing with discrete. So again, we solve this in terms of mathematical notation. And finally, it becomes a rational function. Then we need to find the roots. So here is what the roots are given here in this case. About 1,000 roots. Now I give you some interesting question. Suppose you are given, this is related with the queuing, but I'm giving you a question. For example, so give a word in the English language that has 5 vowels together. So this is the question. I'm leaving it to people who want to think over that. Of course, these days, you can always check on the internet, or you can use your cell. And even when we see what is called Kaun Banega Crorepati, you know that they use cell to answer some question. So here it is related with the operation, related with queuing. So I'm leaving this question. Now, again, some teachers have made comment, the contribution of India to mathematics is 0. So this can have 2 meanings. That means India made no contribution. Or the other is India really introduced 0, how to use 0. Then connected with this, I'm giving you other things. India gave yoga, which has become very popular now. Meditation has become very popular. So that's one other thing I mean. Here you can see meditation and all that. And here are the references, those to meditation and all those things. So here is a little bit of background about me. I was at Kurukshetra University, and when I was a professor there, when I started my PhD while I was teaching full time, I completed my work in 2 years. That means I published about 3 papers in 2 years. Then I applied for postdoctoral fellowship. So Toronto University gave me postdoctoral fellowship. Because I had published 3 papers, they did not ask me, do I have a PhD? I hadn't completed PhD because the minimum time period was 3 years. They will not give me degree unless I complete 3 years. But I got postdoctoral after 2 years. But the Toronto University did not ask me, do I have a PhD? So then I requested the department that let me go and give me a degree after 3 years. That's what happened. That's my little bit about me here. Now, next comes comments by students and researchers. So this is the first student who did, and I talked about this before, and then gives all the comments by the referees, which were very nice comments. Now, researchers also making some comments that Jensen, this, and all the references are there making comments about my root finding. And one of our paper was here, which I did maybe people who are with queuing with Carl Harris. But my earlier paper was before that. And I developed a program and I was even selling that program, $1,000 program. So after I sold about 8 or 10 programs, then I started giving free to propagate the use of root finding. But Carl Harris from USA, so he was involved in root finding. He wrote to me and he invited me. So I went there and then we wrote this paper, which is a very popular paper, which finds the roots. Now, here is what some people are making comment. This Tegal Lukantoni, this is the reference. So he makes a comment that the use if it works, because people had problem with this, then it works blindingly fast. Now, here is the comment made by Henk Times from Holland. So he made a comment that the equation, this root fund equation for this model, again, I told you M indicates Markovian arrival process and D determinant service, C the number of servers. So he said a solution for this, which is waiting time. So we deal with the numbering system or the waiting time for a customer. So he made a comment in his book that a model for this was solved after 60 years. So because the root finding was not being used and they were using other methods, so we now have solved even much more complex situation like GIDC or GID1. And GID1, GIDC, they are related. So now we can solve much. Even later on, I will show you even much more complex solution can be found using root. So here is the comment about from Times in his book. I read with great interest, so he writes to me about my paper. So he makes some comments about my paper and writing to me about that paper. Now here is my first, not the first, the later on student, Brent Fisher, working on another difficult problem. And he solved again using roots, he solved that problem. And there are the editor's comments. Congratulations, a fine piece of it, all those comments by the editor. Now, in around 2001 or something like that, I went to Korea. Korean people, Korean university invited me, and they were having problem to solve queuing problem. And there were 6 students who were doing master and PhD, and they had problems solving those problems. So they invited me. I was there. So all those 6 students then worked under me. I guided. I was there short period, about 6 months. So I guided them. Then, of course, they continued the work with me even when I came back. So here is what the Korean students, analytic work by Korean students. And there are many comments, these will be coming. So then we got the best paper award. This is with one of the Korean students. This was the best paper award. Then, of course, comes the service award. And then there's the award of merit. Now, this may be not readable, but this again, one student sent me his comments, what he learned from me. But this is not, but this is again a comment by a student. And here are something from the principal. Principal made the comment about me, work done, whatever I was contributing. So he made the comment about our principal. Now, this is the story about David Yao. When I came to first time to Toronto, I told you, there was a student working with another professor, Professor Templeton. Professor Templeton and I wrote finally a book, which is still being referred to a first course in bulk queues. So we don't. So this student was there, and now he is in Columbia. He is a well-known professor there who has contributed a lot to queuing. So he was a student. So I guided him in his queuing problem, and then he got the degree, master's degree in to Toronto. Then he went to he got a job there. So he is maybe in Columbia University. So he had made a very good contribution to queuing. So here are the 6 students I was talking about who did work with me. And even when I was back, they continued with working me until they got their PhD or master. So they all are making comments about my work here. That's one. And here is another comment by another student. So he writes that we had a kind of drought, which means they had difficult to solve the problem. Analytically, they had this, but they could not do numerically because the roots are matrix analytic. And matrix analytic is a little complex procedure. And when the roots were not found, of course, people were going in that direction. But now the things are again shifting. People have started using roots. So these are the comments are all by Korean students when I was there. Here is another one doing doctors. And then some comments from India. Here is comments from India. Some student was starting doing paper with me. That's Neetu Gupta from Faridabad. She started doing with me and she writes those comments. These are the comments when we send the paper to Taiwan. So comments about our paper GIM1 or GIMC. Now I talked about this GI geometric M. Now similar to that we have GI. Usually we use capital M, GIMC. Now M here is a Markovian service path, where normally we take as exponential. The service time is exponential. Here the service time is geometric. And earlier I showed you service time was deterministic. Maybe I showed you, maybe it's quite earlier. Maybe I have to go a little back. So anyway, earlier you have seen, we talked about that, GIDC, the service time was deterministic. So going back further now, let's go here. Now here from India, Gagan Deep Singh, he's working with the Punjab University. So I was there with Dr. Gupta. When he invited me, I was there. So he was doing PhD. I helped him in completing his PhD. He has got a job now here in Punjab University. So he's making some comments on the help I gave. And here are the comments from some students. Sometimes we get students in summer. And when they learn says root finding, then they have made the comment. They make those comments. And they get some scholarship. They come to work with me in summer. So here is what our local paper wrote about me. Arms received distinguished award. So that's the paper is here, Kingston Whig Standard is a paper. They write about me in their paper, my contribution. And of course, they write about the award of merit given by Canadian Operation Research Strategy. So the Whig Standard wrote about me. And here is something about the Korean distinguished professor. They called me when I went to Korea. That's the history about that when I went to Korea. And this is now the award I got, which is Mahatma Gandhi Pravasi Sman Award. And there are many who got it. Here is some history about that. This prestigious award we got it. And then the one of only 30. So 30 people got this award, and I'm one of those. And little bit history about more of this here. Maybe you all know Kalpana Chawla. She, of course, an astronaut. Unfortunately, she died. She was in USA, so she got that award. And she is from India, of course, from a place called Karnal. She's from Kara. So she got, and also there's Satyanarayana Nadella. He is CEO of Microsoft, very famous person. He also got it. There are some people who got that. So I got that award too. And now here is a little bit various history, Mahatma Gandhi Award, Best Paper, Distinguished Award of Merit, Distinguished Alumni of Kurukshetra, and there are all those awards. And this is our recent paper, which has been published, and this they put it as the title page of the paper of the journal. That's the title page of the journal. This is the journal from, we recently published this paper. This is the from Switzerland journal. So I can close this, and now I can go to another slide. Yeah. So now we come to queuing, that where the roots method is used. So this is what I talked about earlier, MGY1. So the math behind that is different. So the math takes this form. This is the generating function, which is defined as pi z to the power I, and I0 to infinity is the generating function. Now, we have used a plus because what we do is, instead of at any point in time, because service time is arbitrary, and any point in time we do is call post departure, after departure. Then we connect it to what we call random time at any time. So this is what the generating function, and the generating function, it takes this form. And in this, what generating function are, if you go back to mathematics, if you have a function fz over gz, rational function, so you make partial fraction, and then you can invert it. So that is where the roots method comes, because the denominator, we need the roots. If we find the roots, we can make partial fraction, we can invert it. So just hold. So this is generating function, what is happening here, and how to use the roots. Now, this is the problem. Earlier I talked about GIDC, and then the Times was saying that somebody took 60 years to solve the problem MDC. But later on, I saw GID1, GIDC, and what is this bulk arrival I talked about. So I solved this using root. So once again, you can see the function takes the rational form. Now, it doesn't matter what the functions are. I can find the roots, I can make partial fraction, I can invert. This is generating function. Now, here is a lot of time when I was doing this, I was getting inquiries from different places. One is, say, Australia. One student was doing PhD, and he was stuck with his thesis because he could not invert the transform. Here, what I talked about earlier, Laplace transform or generating function. Laplace transform we invert the same way, and generating function we invert the same way, finding root. So this gentleman was stuck. He had written down, he could not find the roots. So he wrote to me, could you please send us your program, or we will buy that program. So at that time, before that even, I started giving the program free to students to so that spread that knowledge. But at that time, what was happening was Maple was working, even mathematical. So I guided him that how to use Maple, find the roots, and then you can solve those problems. So he did that, he got his PhD, and then after that he got this good service. So this side is covered. I cannot show you this side, but this is the complicated equation he had. So this is again a rational function. Some function in the numerator, something in the denominator. So if you find the roots of the denominator, make partial fraction, and then we can invert it. This is again a generating function. Similar things happen in Laplace transform. Now, this is the various type of things which he's using in his function. It's a complicated function. And then when he does, then he sends me his remarks, thanking me for helping him and so on. Now, then there was somebody from Holland. This is Eindhoven University. He was doing similar thing and he had a problem. So he wrote back to me, here is this equation. His first equation is say F1Z, which is this exponential. His second part is this complicated equation. So what he was looking for is Z to the power P is equal to Fz, where Fz is the product of those two functions I mentioned here. So Z to the power P is equal to Fz is the product of two functions. And now he wants to find the P roots for that function. And now we can find those P. He did that, he solved that, then he again got his PhD and got a good job. So this is the little bit brief history about how the roots are being used. But roots can be used in many other areas, as I mentioned earlier, in algebra, anywhere. Now roots can be found. So this is the brief history. Now, one more thing I have to check is this. So this is the Maple program, which I developed for him to help the Holland student. So the equation is Z to the power Fz. Then Fz is product of two functions. One was F1z, the other was F2z. So F1z is here. Now this notation is being used in Maple. F1z was this exponential, and F2z was this complicated function. This complicated function. That was F2z. So the product is that Z to the power is equal to Fz, where Fz is the product of two functions, F1z and F2z. F1z is this one exponential, and F2 this complicated. So the product finally is this, as Z is F1, F2z, and that becomes finally this. So Z to the power P Fz. So then put equal to 0. That's where we want to find the roots. So I help them, and this is what happened. So I can show you here. I hope it doesn't take too long. So this is using Maple to solve for roots. Unless this gets stuck, I'm not sure. Let's see here now. Well, let's try. I don't want to disturb this. Well, if I touch this, may not. Let's see what happens. Yeah, this is the point where it has to work, but something maybe not. Let's see if I can. So this is the point which should be working, but some problem happened. Okay, let's try leave this. Maybe no. Okay. Okay, we say no. It still doesn't go. Oh, yeah. So that program maybe now have to get that. Let's see if I can get that program. Let's just. Let's see, root finding here. So let's see if it works now. Yeah, it's going. So it may take half a minute here or something. Yeah, it's done. So here are all the roots, and then you can see the graph here. Here are all the roots. So this is for the Holland problem, very complicated, and that's how the roots are formed. Because once I told you the functions are rational function, or maybe rational doesn't mean it has to be a polynomial. It can be a transcendental function, whatever. We find the root, make partial fraction, and then invert Laplace transform or generating function, similar procedure. The initial math is different. Once it is done, it becomes a rational function. After that is the root problem. But comparison has been, I showed you earlier, Gagan from Punjab University. So his problem, I gave him problem. So his problem was to compare the two methods, matrix analytic and the roots method. The roots method takes very little time compared with the matrix analytic. Matrix analytic was introduced by Newts, because as I told you earlier, Candle, Kleindog, everybody was saying roots cannot be found. So that's how they shifted. But now the roots method takes over the matrix analytic method. So it's very powerful now, very difficult problem can solve it. And a lot of students are working with Dr. Gupta at IIT Kharagpur. So Dr. Gupta visited me, so he picked up all that. Then he has trained so many students in India. Of course, I have been training a lot of students here too. So this would be, the last thing I can show you is maybe was one more. Yeah, maybe I can end it here. So this I can say, thanks for listening to this question. And if you have any question, any general question, you can raise the question. That's all from my side.
Thank you, Professor Chaudhary, for your nice presentation. So Professor Chaudhary has described the basic things of queuing theory and how different types of mathematical programming techniques like Mathematica Maple has worked. And also he can solve, he solved different types of transcendental and non-transcendental polynomial equations, algebraic equation by some queuing technique. Through some packages like QRoot and QPack. So thank you, Professor Chaudhary. So from the audience, if you have any questions, maybe we can consider one or two questions, because due to the shortage of time.
Particularly this, the root finding can be used anywhere. Of course, I'm using in queuing. In all other problem, many other problems, you can use the roots.
Yes, yes.
Okay, go ahead. Any question?
Yes. Yes.
Sir, I have a question. Sir, I have a question. We are having a first order condition, which is a transcendental equation basically. So can we show that a root exists, a positive real root exists? So is there any method to show? We are using Bolzano-Weierstrass theorem to show, but is
no
so,
the Maple program? I showed you that Maple program. You write the equation. Maple program now find the roots.
okay.
Yeah,
Okay.
Maple. Lot of this same problem came up from say Holland, from Australia. I told you. So now, luckily, of course, before I told you, I was selling my package. Then first I started giving free. Then when I went to Korea, there I came to know that Maple was working. So now Maple works. You can learn from this Ghosh. He will tell you he's using Roots. All other people in India who got training from Dr. Gupta using it. So Maple program now works, and you can ask him. He can guide you how to find the roots.
Okay, sir. Thank you, sir.
Most welcome.
Thank you. Thank you.
Most welcome. Most welcome.
Thank you.
All right.
Hello, sir.
Yeah.
I have one question. When we have the TPM for any queuing system that is general structure, can we use the roots method to find the solution for the stationary probability vectors?
No, roots method is if you have a polynomial, okay, one, or you have a transcendental function. Say in polynomial, you have sine, cosine, exponent, anything. The root methods will work. And I gave you the code here, how Maple is using, but it's very simple. Now you can ask Ghosh, he can guide, sweet Ghosh, he can guide you if you want to use Maple.
Okay, thank you, sir.
Okay, most welcome.
Okay, thank you, Professor Chaudhary, once again for your nice presentation. So a big clap for Professor Chaudhary, please.
All right, thanks a lot. Okay,
Thank you.
okay.
Yeah, so we are now going to, I thank Professor Shamarjit Kaur for chairing this session. And we are going to have a tea break for just 10 minutes. And the next session will start here. Just a minute. Okay. Yeah, so a correction. We are going to start the next session here. Start of the next session, and then we are going to have tea break later. Okay, so I request Professor Manoranjan Maiti to come on to the stage to chair the next session. Okay. So we welcome Professor Manoranjan Maiti on the stage, and we have already introduced him yesterday. So I will right away request him to start off the proceedings with this session.
Good morning to all. Our speaker is Dr. Gautam Banerjee. He is a data science. He is a data science and AI practitioner with 2.5 decades of managerial and leadership experience, with couple of patents to his credit. He is the director of Business Bravo, which offers consulting and project services in the areas of data science and data engineering. Business Bravo won the Excellence in Analytics Award from NASSCOM in 2015 and was a finalist for Red Herring Top 100 Asia Companies in 2017. Selected in CIO Insider's Top 10 Analytics Solution Providers in 2018. Covered by Boston Herald and NBC WRDE in 2020 and featured in Forbes Data 2021. Now, Banerjee, I request you kindly start your valuable lecture.
Yeah, thank you, Professor Maiti.
It is 25 minutes for lecture and 5 minutes for questions.
Yes, sir. Thank you. Yeah, so very good morning to all the participants and audience. Also thanks to Operational Research Society of India for arranging this seminar and for Heritage for supporting and sponsoring this. So now, as you can see, I'll be talking about a standard, ISO standard, for big data analytics, right? We are speaking about big data analytics since yesterday. A lot of analytics, a lot of AI models, algorithms that we have seen across. However, this is a standard from ISO. A lot of us may have heard the ISO for ISO 9000, ISO 27001 for data security and other stuff. But then this is something on big data analytics. Now, so this is basically talking about standardizing the implementation of big data analytics across organizations. It can be a government organization, it can be a corporate organization, which is private or publicly held, and the challenges. So let us, see this. So while on one hand we have got, and since yesterday we are seeing lots of theories, lots of formulations, applications, adaptations onto the technology side of it. But what you are seeing on the screen right now, and in a couple of slides more, you will be actually seeing all the failures. So this presentation, is a bit unique. I'll talk more about failures of artificial intelligence and big data analytics, rather than boasting about any particular algorithm or the success of it. In most of the events and seminars, you will go and see that CIOs and CTOs will go up and then talk about success and what potential and opportunities AI ML has, right? However, we all know that. I mean, and then mostly, these are applicable for digital companies, but we are going to talk about the practical reality on the ground. So what you get to see here is basically something from the Forbes magazine dated 7th of November. So it is just last month. It is not dated like 7 years, 2 years back, right? And it talks about, the data science, failures out there. This one, is from a very popular magazine called as Computer Weekly. It again, talks about, the failure modes of, different data projects, right? Interestingly, if you see the date, I've circled the date with, a red marker out there. This is also dated on 7th of November. In fact, I had a speech out there at Imperial College that was actually on 7th or 8th. And, that's where I, prepared this slide actually on the same topic, right? Now, while these are very latest reports out there, let us go back in the past, right? Now, this is from, Gartner, as you can see, and this dates back 7 years. So that gives us the time period, right? So from around 2014 onwards, you have got either, different magazines for CIO, CTOs, which are very popular in the world, starting from Forbes to Gartner. On one hand, while we are developing these algorithms and adaptations, and we are talking about these applications, on the practical world, real world, if you take away a few companies which are very digital company, we are not talking about Google, we are not talking about Facebooks of the world, but we are talking about conventional companies like the steel companies, like the manufacturing companies, like the service industries, banks, and they are trying to implement these algorithms, these kind of projects. They're trying to embark upon these kind of projects. There's a huge problem, and unfortunately, this is a hard reality. No one talks about it when you are on the dais. More than 50% of the projects do not complete. 30% to 40% of the projects, and 40% of the projects, around 45% of the projects complete. And then, out of that, maybe, 30 or 25% of the project actually, gives a needle movement on the top line or the bottom line of the company. Now, please remember, this is very important, that while on one hand, we, keep on advancing our computing, technologies and power and algorithms, we also have to understand the practical reality on the ground for 90% of the industries, which are conventional industries. While Google and Microsoft may have a large chunk of the, the pie of the financial pie of the industry, but then 90% of the industry actually is the conventional industry. We do not have information technology or operations research techniques for IT companies, but these are actually meant for conventional industries, right? And that's where we are talking about. Now, I'll reiterate, what is there, what has been told by the Gartner Research Director, that to succeed, you must develop a viable strategy to deliver the business value from a big data initiative, then map out and acquire or develop the missing and specialized skills that are needed. And once the strategy and the skill priorities are addressed, then you can move on to big data analytics. So let us talk about some, couple of scenarios for us to understand where, we fail. And it is important that you will see actually in the previous slide that Gartner says that most of the failures never happen because of technology or algorithm, right? These failures are actually happening because of different organizational blocks, different kind of facets of organizational, departments not being integrated, not having a common kind of a goal, the lack of change management that needs to be done, as well as a lot of issues with the upstream and the downstream integrations of data. So we'll talk about all these things. Let me give you, one or two examples of some of these, initiatives that we have seen struggling. One project was actually done across part of Telangana and Tamil Nadu. I'll not name the company. It's a very big company, worldwide known, and it was an initiative part of Niti Aayog. And in 2017, we get a report saying that using AI, AI-based agricultural, decision-making systems, it was a big success. How was the success called out? The success was called out by showing the yield of the agricultural crop. So the problem statement that was solved was basically that which crop has to be sowed at what time of the year exactly, so that the crop yield is maximum. So that was the problem statement which this company started this initiative. Now the point is that yes, that was started, but then the proof was given saying that compared to the last 2 years of time, the yield was much more. First of all, 2015 there was a drought. 2016 it was a recovery from the drought. So obviously 2017 data will actually show you a better results in terms of crop yield, right? That was, that is something that, we pointed out from Niti Aayog, right? And then what happened was basically that this kind of an algorithm based things will only work when there is a heterogeneous system. It cannot be homogeneous. So if you take a particularly, vast, land surface out there for any demography, right? And if you decide that technically, which crop to be sown at what time of the year to give the maximum yield, the yield will be maximum maybe, because of the, the AI algorithm that is being built and trained on moisture content, the chemical contents, the rainfalls, and everything else, out there in terms of wind and temperature and everything else. But the point is that, if you follow economic basics of economics, then there will be a problem in supply and demand, right? If everyone, now starts planting or growing peanuts, there'll be no price for peanuts. So in this case, it's a governance call. It's a decision oversight, and it has to be, done in a more heterogenic manner rather than a homogeneous decision. So while, at an individual level and in silos, we may be very excited with individual algorithms, but please understand, implementing AI and ML in the real world includes a lot of other management, context, which are very important. Otherwise, there can be a catastrophic, disaster as well, right? So that is one of the things. Let's go back, to, the autonomous cars. We are very excited, and at times, every, once in a month or every once in 3 months, there's some news when we say automated cars will be there, no drivers will be needed. And in third world, we talk about, job loss, but in developed countries, they're very excited about it. right? In 2018, we go to, Sunnyvale. We get, some of us, we get invited to Sunnyvale at Google office out there where they're working on this particular stuff, right? On autonomous cars, not Tesla, but Google, I'm seeing Sunnyvale office in Silicon Valley, right? And for almost couple of days, we discussed just one problem and try to understand what I'm saying. A particular scenario we discussed for almost 2.5 days, almost 20 hours, different experts from across the world. And we discussed saying that assume a case that a child is playing football on a ground. The ball passes onto the road. The child comes to pick it up from the road. An autonomous car is getting driven. It is, driven at around 80 miles per hour, which will be around 120 kilometers per hour in India. And there's a mom who is driving the car with a baby of around 9 months, 8 months in the bucket seat. What are the options? If the child comes up to pick up the football in front of the car and is hardly 100 meters or 70 meters away, there are 3 options. One option, save the kid, divert, or save the kid, or press brakes at the maximum level of force or torque. Correct? What can happen is that in spite of 6 airbags in the best of the cars, from a safety feature perspective, even the airbags can cause suffocation for the child, and the child may die. When I'm saying child, I'm saying the baby, who is 8 months old baby, right, sitting in the car. So that's one possibility, that you save the kid, but there can be a huge impact inside the car. The the airbags will blow up, and there can be a suffocation for the baby who is maybe 8 months old, or maybe even 1 year old, right? What's the next option? Next option is, okay, try to save the baby inside the car, save the child on the road as well, and apply the brakes with some kind of balanced force, but divert the direction. Now at 120 kilometers per hour or 80 miles per hour, if you divert the direction, obviously you'll have less control on the car, and there's a high possibility that you're going to injure people who are walking on the alleys beside the roads, footpath, as we say in India, right? What's my third option? Third option is that try to balance it out and see, what can be done. And that's fuzzy logic, right? So what I'm saying is that while we are very excited about all these advancements, there are huge challenges out there in implementing, AI, ML in the practical world. What about the decision oversight? What are the risks, involved? What about over reliability? What about transparency? What about bias? And we all know about it. It's not that none of us know about it. A lot of work is actually already happening on that. But I'm just giving you live use cases where these are, problems out there, right? And and failures happen because of different reasons, right? One more thing that I want to call out from the industrial perspective. So a huge metallics company in India, based out of some of the foreign entities as well. We get a project as a company saying that, okay, why don't you come and help us in optimizing or improving the process, right? What was the process in the steel industry? It's a very simple summary of the process that I'll call out for you to understand. It's basically the core, the heart of the steel industry is a metal blast furnace, which will basically take some inputs as burden charge, iron oxide, ferrous oxide, manganese and zinc and other stuff. They'll melt it at an outcome of 1650 to 1700 degrees Celsius. It comes out as basically molten metal. Just looks like gold. There's a froth on the top. You take that out. There's a slag. Send it to the cement industry, and then take it out. Put them onto something called as ladles, buckets, and then you either do a centrifugal casting for ductile iron pipes. Initially they're brittle. You take them through annealing process, and then they become ductile, or otherwise you basically cool them off and then produce long bars or short bars, as you can see in different steel plants, right? But what happens in a metal blast furnace, the ignition is actually from below, and you put the charge from the top, and the height is around 3 stories of a building. I'm talking about 1 MBF. So if you go to Tata Metaliks plant at Kharagpur, you get 3 to 4 MBFs. If you go to Tata Steel in Jamshedpur, they have many more. So you can understand the size and the magnanimity of that, right? Now what happens is that if you actually pour the charge from the top, the ignition can stop. Why? Because of the fine particles, it can stop oxygenation. So what happens is that to enable that, you need to do something called as create something called as sinters, chunks. So there's a sinter plant. In the sinter plant, what happens? The ignition starts from the top. So it's a belt. You put the charge, a mix of ferrous oxide, manganese, zinc, and other stuff. You put the ignition on the top, and then you move the belt and you suck it from belts, right? I mean, from they're huge very powerful fans which will run so that they will suck the air, and it's like a smoke. So the ignition will actually the light will actually come down, and the belt speed is adjusted in such a way that at the end, when the ignition at the end, the belt turns around, correct? So it will all fall, and because of the melting process, they'll form chunks, which are the sinters. There are physical and chemical characteristics which are again checked for them, like plus minus 18 millimeter in size and all those things, which will then be eligible to be put into the metal blast furnace. I'm just telling you in short the process of any generic steel plant, right? So we were basically said that, okay, there are different kind of variations in my input parameters. What are my input parameters? Maybe ferrous oxide. So ferrous oxide, if it's coming the iron ore basically, right? If it's coming from the Khonboni mine from Odisha, it will have a particular chemistry. If it's coming from Bermo, from Jharkhand, the chemistry will be slightly different. If it's in the monsoon season, moisture will be more, so you need to give more coke. If it's in the dry season, moisture will be less, so you need to put less coke. Then if it's a Chinese coke, you have to put more. If it's an Australian coke, you have to give less, right? So there are different kind of input parameters and process parameters. So what was the challenge given to us? We were said that given the variation of the input parameters, can you build an algorithm to change the process parameters so that my outcome parameters lie within a range, so that my maximum acceptability of the centers will happen, which will go into the MBF. So minimize the losses, right? Because they had huge reductions. So we obviously built different kinds of adaptations of regressions and all those things, and eventually solve the problem. And it was built into a system wherein based on the input parameters, process parameters automatically changed, and then they got something that is within a range with some acceptable accuracy, right? The point is that when we started the project, for the specific company, I'm not naming the specific company here, I just took examples of these industries like Tata Metaliks and Tata Steel, but I'm not calling out still the company's name here. But then when we started, we were told that all the data is there for the last 5 years. Now, it is actually true. They had all the data. But now understand how they got the data. So for a single timestamp, they've got a spreadsheet out there, and they have got all the input parameter characteristics. They've got all the process parameter characteristics, and they've got all the outcome parameter characteristics. That is meant for one single timestamp. The point is that, can you regress that? Can you build a model out of it? You simply cannot. Why? Because the sinter plant process itself takes anything between 35-40 minutes of time to 55 minutes or 1 hour 10 minutes. That means I have to now basically have a lag of those things, check those lags practically from the shift operations log out there, and then arrange the data. Otherwise, it's not a linear data. Otherwise, I cannot build a model, right? Now, these are, I just took a couple of examples saying that while we have enough algorithms, and we are getting algorithms every day, new algorithms, new packages, either you talk of R or Python or Kotlin or Julia. The point is that at a practical level, when you go to conventional industries and try to apply these things, there are many, many, many constraints out there. And that's why these projects do fail, right? I'll talk about the standard, which tries to have a method behind this madness of minimizing the failures. But before that, I'll talk and say something about standards itself, right? So what is basically a standard? It is basically a standard is useful because you can reuse, you can share it. It is usually done with a lot of collaboration. A standard is never called a standard under either IEEE or ISO, a world which is done alone. It's consensus based, so you've got a lot of trust and adoption is very fast. I mean, that's the basic need, right? What are the forms? They can be technology, framework, methodology, use cases. Many of us, if not everyone, will be knowing something like CMMI. So CMMI is basically a framework for software development lifecycle, right? It's a framework. It's not a technology, by the way. But IEEE, comes up with a lot of technologies as well, right? Now, what are the means? Obviously, publications like we are seeing since yesterday. A lot of publications are also standards because, people will reuse them, right? People can learn about them, the kind of work, they can extend that work, adapt that work, reuse them, with, formal recognition, references and all that. There can be patents as well, wherein you again disclose that. There's a very important part of the patent called as IDF, Information Disclosure Form. So you disclose what is there as part of the patent, but then patent allows you to hold the rights of it for the next 20 years. After 20 years, it is again open to the world. So again, anyone can use it, right? And you've got standards like, ISO and IEEE standards, different kind of certifications, and also regulations or legislations like GDPR compliance and other stuff for Europe, right? So these are different means of standards. And what are the source? Obviously, different kind of forums, bodies, national, international, countries, participate out there to form these standards, right? Now, here you can see, 4 standards. I will be highlighting on ISO 24668, and I'll call out what is that. But I'll also refer to 5259 series. It's called a series because they've got 5 parts. I'll briefly talk about it. 5338, which is AI lifecycle methodology, and then 38507, right? That's governance, and that's of immense importance, right? So even before that, if you can look at the bottom of the slide, there's some acronyms written out there, right? These may be Greek or Latin, for many of us who are not involved into standards, but let me just explain you the process of how a standard is getting formed. So first, when you propose a standard, it is called as new work item proposal. It is hence called as NWIP, new work item proposal, and that gets into the ballot. So I belong to the ISO SC 42, Standards Committee 42, which is for artificial intelligence. It's one single committee having 38 countries out there. So it goes into a ballot, and minimal, there are some thresholds. So minimum, so many countries will have to actually say yes to it while you actually cross that stage. Then comes the stage of WD, which is the working draft. And again, the working draft will get into a ballot to get into something called as a committee draft, CD. And then the CD gets into something called as drafting standard. And then FDs is final drafting standard. And after that, something is called as international standard. Usually every standard takes, we have not seen any standard in the world of ISO or IEEE, which has happened before 2 to 2.5 years of time. And maximum is 3.5 to 4.5 years of time. If you take a median, I'm not talking about mean. If you take this is a technical audience, so I'm talking about median. If you take a median, you will see that average standard takes around 3 to 3.5 years. With a 95% confidence interval range, I'm talking about, right? So any which ways, but then so what is 24668 that I'm going to talk about? It will refer to 5259 series. So what is 5259 series? 5259 series is very important and critical for us in terms of data. It actually takes different aspects, facets of data, and calls out the standard. It talks about the terminologies in part 1. It talks about the characteristics of measure of a data in part 2. It talks about measurement of those kind of data in part 3. It talks about data lifecycle in part 4. And these are very critical because we all know that if we do not get the right data, finally, it is not going to help the business process, because finally AI or ML is not for the sake of it, but the AI ML is for the sake of the business. You have to finally, get some recommendations out there, which will, if actioned upon, will move the needle on the top line or the bottom line of the business. Otherwise, it doesn't make any sense. Now, so data life cycles, you have got data requirements, you have got data preparation, then you have, data provisioning, data, you have, then data consumption, and then you have got data decomposition, right? So those things are called out there. AI lifecycle methodology is very important because many people think that it is an extension, AI ML project is an extension of an IT project. No, not at all. IT projects are very deterministic in nature. These are very research-based projects. You need to follow a different methodology, and that is called out there. I'll not get into the details of it. And then 38507 is basically about the governance, like I was telling you, like transparency, bias, decision oversight, reliability, all these things are covered in 38507. Coming to 24668, that is something that I'm going to talk about. So this is interestingly not only a standard which is very critical for the world. It has been published almost now, I think 3 to 4 weeks back. It took around 5 years of time from 2018 till 2022. But there is a special technical specifications TS and an assessment standard, where you take the standard and you can assess the capability of the processes or an organization, right? This is first of all the first assessment standard in the world for AI. The second biggest important thing is that first time in the Indian IT history of 40 years, India is defining a standard for the world. So we have conceptualized it, we have socialized it, we have taken it to IEEE and ISO. We have led this, so I was basically the editor and project lead for this for the last 5 years of time. We have conceptualized that, from our company. We got huge support from BIS, Bureau of Indian Standards, Government of India, located at Manak Bhavan in Delhi. And then there are 18 countries who contributed towards this standard. And there are 38 countries who have finally endorsed this standard. And normally, we have a assessment and we, celebrate. But here the importance is that we are defining the standard for the world, which is the first assessment standard for AI and ML, right? So that's the criticality of it. Now let's take a deep dive into what is the standard. This standard is again trying to have a method against the madness for working around the failure modes of project implementation in organizations. It is not talking about individual algorithms. It is talking about, stakeholders, starting from change management, what will an AI ML algorithm will do? If you talk about e-commerce platform, you say recommendation engines, depending on the buying trend, right? The recommendation engines will have to be implemented. It has to go back, someone has to take a decision saying that, okay, I'm going to take this with this kind of an accuracy and I'm going to use this either in an e-commerce platform or even if not an e-commerce platform, somewhere else. You can have a forecasting model for inventory management, for stock out analysis, but someone will have to accept it and take a decision on it because you have to make it actionable. Otherwise, it's not going to have the little movement. So huge levels of change management is needed. As I said, you may, start on a project, you may get only, data from one warehouse or one center because some of the change management was not done, So the change management has to be done. There'll be a huge integration between the IT systems because all the data will come from either a data lake or a data warehouse, or some other systems of MongoDB or SQL or Oracle systems, right? So upstream, downstream linkages. So first is the organizational stakeholder processes on the right-hand side. You will see 5 process groups out there. Each process group has got its own processes. Overall, there are 19 processes spread across 5 process groups. Each process groups are important out there. You have the competency development process on the left-hand side in the middle row, which is very important about the skills. How do you plan to upgrade the skills? Will you do everything in-house? Will you actually have external consultant out there? Will you tie up with, good institutes who have got, research collaboration, facilities at times? In the middle is the data management process. And again, data is the heart of everything. So there's a lot that I can talk about data, but I'll refrain myself from talking much. but it includes, data strategy, data architecture, data measurements, data dimensions, adequacy, lot of things, right? And then you have got the analytical development process. So analytical development process will include, a lot of these algorithms, selection of algorithms, the criteria, the baselines. Many a times you will see that you will, proceed with an AI/ML project without doing a proper baseline. And now we say we are going to improve. So I'm going to forecast something for a Dutch company for wind energy. Now, how do I know whether my, forget about the algorithm. So you can use a neural network, you can use an ARIMA, you can use an Armax, but then how do you know that, your project is successful? So you have to have a baseline saying that, okay, what is my baseline of accuracy right now with a certain margin of error? What is the time lag that you are forecasting, right? So you're forecasting for tomorrow or you're forecasting 1 week down the line, right? And are you forecasting with a lag for 2 days or 1 day? So the frequency, the lag, these things will have to be baselined. Otherwise, there's no point. And then we have got the technology integration process, which is very key because for a live system, when you built in these algorithms of, developed in R or Python into the system, you have to have huge upstream and downstream integrations out there. You call APIs or something else. You have got, different kind of macros. And then last but not the least, the enterprise data mart, right? As I was saying, so data warehouses plays a very important role. You can have a DWH or, the more fashionable word these days are data lakes. It's not always needed, but then people are very, fascinated about data lakes, but it can be a hybrid model as well. You can have a structured data along with a non-structured data. And, there are different schemas out there as well. So that's the 5 process categories with 19 processes out there. On the left-hand side, you have got, different things. One is called PRM, process reference model. Then we have got something called as, a process measurement framework. And then we have got PAM. So we take help of process reference model, PRM, and measure the framework, and then, do the assessment, right? So what is that? Every process, here there'll be 19 processes. Every process will actually have a context, purpose, and an outcome. There will be attributes and information products that I'll show you, and there'll be a way to measure that. And then finally you will assess that, right? So give you a glimpse of that. Obviously it's not possible to take you, through the entire thing. So it's a huge, document out there, more than 100 pages, 150 pages. So this is calling out one of these process out of one of the process categories. And it is called as a data identification process, right? And it is from the process group of data management process group. And you can see there, so you have to put out the context, the purpose, the functions, and the outcomes. And outcomes are indexed here in ABCDs. So these are the specific outcomes that should happen. Now, what happens is that you've got some base practices. So the top table that you get to see, calls out these base practices that should happen for that particular process, which has got its outcomes and purpose and context. They are called as BP1 to BP4, right? You can see this base practices. Base practices, now you can see on the right hand side, have again got the reference of the outcomes, because if you recall, the outcomes had those indices of A, B, C, D. So each of the base practices now on the top table actually refers to the outcomes which have been there in the previous table. And then you have got the information products, which are basically artifacts which can be assessed, to understand the capability level of a particular process, right? That's how it goes on. Assessment I've called out. So it's basically, PRM, PAM, and the measurement framework all together. Finally, it is going to let you know not only the assessment on a scale of 1 to 5 or 0 to 5, there are 6 levels, but the important thing over there is the outcome, which is trying to give you a roadmap of where you are in terms of your maturity and capability levels of, different functions, different processes, how to, bridge those gaps, and, how to identify quick wins out there, and maybe, have a priority list of the use cases of big data analytics. That's the outcome that should ideally happen when you assess this, right? So that's it, from my side. Any questions or anything? I'm open for that.
Very nice lecture. Mr. Banerjee told his experience and what he faced during his work, and how to overcome those difficulties. And any question from audience, please? Mr. Banerjee, is it these standards are required for making a patent or?
No, I mean, this is a very good question. Thank you, Professor Maiti. No, so basically standards, so you decide basically that, if you want to keep it open, for the fraternity to be used. So if you actually file a patent out there, then, it is not called as ISO standard, but the ISO standard can refer a patent. But when you actually decide to, we decided as a company that we'll give it to the world, right? So this cannot be patented anymore. But then if we think that, okay, there's a patent that we have filed, but there can be an adaptation from there. So we can do a standard where the standard will refer to the patent. And it actually works like a GPU GNU license. So in the open source system, there's a GPU GNU license. If you have a GPU GNU license, any adaptations of that will also be an open source product. But then if you have an MIT open source license, so the MIT open source license allows the adaptation to be patented, but not the initial work. So it works like that.
Actually, in our theoretical research, we do the modeling and we do assume the methods for AI or ML, and we don't consider about the standard, or we don't consider anything.
No, I was talking to Professor Kaur as well. So maybe we can talk more, but the world needs us. So they are asking for participations and contributions, because once it is standardized, it reaches to more people and to the industry. So I think it is going to help.
Very good lecture. Thanks to Mr. Banerjee. Let us join hands with me. Thank you.
Well, thanks, Professor Banerjee, for the enlightening lecture. And we now express our appreciation of our speaker's participation in this session by offering him a small memento. And I request Professor Shamarjit Kaur to come to the stage and offer it to him. Thanks, professors. And we have already offered Professor Maiti our memento. Thank you for chairing this this session, Professor Maiti. And now we have the sessions upstairs in 6th floor of ICT building. So you have the schedule with you. So we will now move to the 6th floor of the next building, ICT, where I think you have your presentations, paper presentation sessions. Okay. So but just a moment. Before that, some tea and refreshments are offered in the executive hall, just beside this auditorium. So you can have your tea and then go to the 6th floor.